Hey guys, we're going to attempt to finish up chapter 11 here. Now, a couple of things are working against me today. First, suffering from a bit of the COVID, so we'll see if my voice can hold up. This is a really long section. Um, so hopefully I can get through it before my recorder cuts me off. That would be the other issue that's working against me. My recording stuff is being naughty. All right, 11.2. We're going to be testing tests about the difference in the means and also what happens when we have a matched pairs design. How do we adjust for that? So, like I said, very loaded lesson. Let's get to it. So just like we saw with proportions, when we look at difference of means, it's going to be the difference between the means is some sort of hypothesized value, typically meaning the difference is 0 for the null hypothesis, meaning that the two means equal each other, so there's no difference between them. And then our alternative hypothesis is going to be either not equal to 0, meaning it's different, or greater than or less than, depending on how they define the wording. So we still have to check our conditions. The random condition, remember, refers to having independent random samples if you're sampling, or if you're running an experiment that your two groups are assigned randomly. And then the 10% condition, again, only applies when you're sampling without replacement. So if you happen to be looking at a problem that's an experiment, do not mention the 10% condition. It's not appropriate. And then for the large enough condition, which is what we've been calling it, remember it's not large counts because these are means. You're looking for essentially the central limit theorem. So you have three things you can look for. First, if the general population is known to be normally distributed, you're good. If the sample size is 30 or greater, you're good. And that happens for both of the samples that you're taking. And if neither of those things are true, or at least unknown, then what you have to do is draw a distribution for the sample data. Unfortunately, you have to do it for both of them, and then to determine whether or not the data has any outliers or any skewness that's very strong. There's an example coming up in here where some of you might argue there's an outlier, but they're going to say no. All right. Remember, we can check for outliers technically, but you just go with your gut. So what we got here? The mean number of hours Americans work in a week. Has it changed? So they're going to compare the mean number of hours from 1975 to 2014. And the question is, do these data give convincing evidence at the 5% significance level that there's a difference in the true mean number of hours worked per week from 1975 to 2014 for Americans? So what they want us to do first is state the hypotheses and then make sure we define the parameters. We've learned our lesson on that one, haven't we? So the null hypothesis would be that there is no difference. So the mean from 2014 minus the mean from 1975 is nothing. Oh gosh, I feel like my voice is going. The parameters, the alternative hypothesis is that it's different, right? So that the two means are different from each other. So we're going to use a not equal to symbol. So the mu sub 1 stands for the true mean hours worked by per week by Americans in 1975, and similarly for 2014 for mean 2. So these were random samples that they took. I think they mentioned that earlier in the problem. And then the 10%, yes, those numbers are definitely less than 10% of all working Americans in both of those times. And then both the samples were greater than 30, so we are large enough to say that we are approximately normal. So same standardized test statistic formula that we saw before, but of course, because it's the difference in two samples, it's going to be a little more complicated. So this is the t distribution test statistic for the difference in two means. So you'll notice the statistic is the subtraction of the two means in the order that you defined in your hypotheses, minus 0 because the parameter difference is 0. And then remember, when you're trying to combine two standard deviations together, you have to combine the variances. So you'll see that they use this formula because this is the standard deviation squared, which is your variance plus your other variance, and then square root that whole thing. That is kind of sort of found on your formula sheet. So we need to do some investigating about where our formula sheet can be our friend in this section. Now, to determine what the p-value and the value for the t-score, if you want to call it that, is going to be, and also the degrees of freedom, you can use technology, yay, or you can use the less fun way, which I think is using the table. Now, if you're using the table, the degrees of freedom is going to be based on the smaller sample size. And then remember, the table has its limitations as well. So we're going to see an example coming up in a moment where, like, the sample size is I don't remember, but it's something, large, but the next one down in the table is like down to 100. So it's frustrating to use the table, I find, especially when we have such great technology around us. So that same problem about working Americans from 1975 to 2014. So explain why the sample results give us some evidence for the alternative. If you remember, the alternative hypothesis is that the mean number was different. So if you look at the average, so right here is the mean for each of the samples. They calculated that already, so that was nice. But when you subtract them in the order that we defined in the problem originally, we found out that, yeah, they are not the same. There is a difference other than 0. So that is some evidence towards the alternative hypothesis. Now we have to find if it's convincing evidence. All right, I'm going to pause a moment and drink because I am dying. Got me some Chick-fil-A water with that crunchy ice. I'm trying not to chew on the microphone so I make you all deaf. Okay, shout out to Chick-fil-A. Thank you for your weird ice. All right, part B, we're going to be finding the test statistic. This would be doing it by hand. It's not terrible, it's just not fun. So that same difference is the statistic that we just found. So that 2.94 minus 0 is still 2.94. And then here you'll notice they took the standard deviation from each of the samples, squared them, and then divided them by their sample size. And this is the variance divided by n, variance divided by n, added together, square rooted, and that's how the formula works out. Ooh, lovely. I'm going to be honest, guys. I am never going to do that by hand unless I'm absolutely forced to. We're going to be using our calculator on these. Now, with that being said, don't tune me out because you never know what kind of a weird question you're going to have. Oftentimes, the multiple choice sections will give questions like, which of the following is the correct setup to find the t statistic? And you have to understand how the formula works to get that right. All right, so that's the t value. Now you're going to find the p value. Remember, the degrees of freedom can be found with the calculator, which is the way we're going to do it, or you can use, the smaller sample size and using the table. So let me get rid of the one first that I'm not going to use, which is the table. So out of the two sample sizes, 764 is the smaller one. So ideally, our degrees of freedom should be 763. But if you're using the table doesn't go to that number. So it goes to 100 and then it skips to like 1000 or something. So you always round down on the table using table B to be more conservative. So they would make you use degrees of freedom of 100. And then they're going to get this p-value. Remember, it was two-tailed, so they had to double it. Now let me tell you what's much better, and this is the way we're going to do it. This whole problem could have been done with a two-sample t-test, which I'll show you in a minute. So a two-sample t-test means that you can either enter statistics or data. In this case, we'd enter statistics, and we would enter the mean and standard deviation in the correct order, and boopity boop boop, magic calculator. It's going to give us the t-score, the p-value, and the degrees of freedom. And I know it's like a mystery to you as to like, oh, where did this number come from? Don't worry about it. It is nothing that you're going to have to hand calculate. Just know that it's there. Now, using that better, because the technology does give you a better p-value, a more accurate one. 0.000, yeah, that's small. Okay, in fact, it's smaller than our significance level of 5%. So we're going to reject the null hypothesis and say there is convincing evidence that there is a difference in the true mean number of hours worked by Americans in 1975 versus 2014. All right, so that's they did a by hand problem essentially, but yeah, we are not going to do these by hand. I'm going to be frank with you. We have a $150 machine at our disposal, and we have so much to worry about in this class and on this test. So when we're going through the procedure for a t-test, when it's two samples in particular, we are most definitely going to be using our calculator. So, what do we got going on here? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a comparative experiment. All right, so wrap your brain around the fact that we have an experiment. We have 21 healthy men as subjects. They were volunteering to take part in this experiment. They were randomly assigned to two groups, 10 who received a calcium supplement for 12 weeks, and a control group of 11 who received a placebo pill. All right, double blind, and then the response variable that they measured was the decrease in systolic blood pressure, which is when you get your blood pressure, it's that top number, like 120/80, it's the 120 part. So for a subject after 12 weeks, so after 12 weeks they measured it. Okay, I can read. Now, I hate the way they design this data. An increase appears as a negative number. What? So here's the data. So group 1, this first patient, if you want to call them that, has a 7, which means that their top number decreased by 7. I know. I get it. I understand why they did it this way, but I'm like, why? Oh, my dyslexia just like flared. So this next patient in this group has a -4, which means that there was an increase in their blood pressure for that top number from the week 1 to week 12. All right, here goes. So do the data provide convincing evidence? Blah, blah, blah. Okay, we got to go through the whole inference procedure. So let's state the null hypothesis. Is that mean sub c minus mean sub p, mu I should say, sub p equals 0. So down here they define who's who. The mu sub c is the true mean decrease in systolic blood pressure for healthy men like the ones in the study who took the calcium supplement. So this is the group that took the calcium. This is the placebo group, and we're measuring the mean decrease. Now this is where I have to really stop and think about how they define this. A decrease is indicated by a positive number. So if we're trying to show that the calcium group has a better decrease in blood pressure than the placebo group, then that means calcium should be greater than placebo, right? They should have a greater decrease. I know, dyslexia, I know. So that's why they set this up as C minus P is greater than 0. It took me a minute to wrap my brain around that one. I think you can imagine why. So we have the hypothesis set up properly. This is not a typo. This is just really hard to understand the way they worded it. And we're testing this at a 5% significance level. All right. Unfortunately, okay, well, first of all, the name of this is called a two-sample, no surprise there, t-test, okay, for the difference in the two means. So they were randomly assigned. Notice we didn't say anything about sampling because we're not sampling. We did not check the 10% condition because it's an experiment. And unfortunately, the sample sizes were very small, and we don't know about the general population as being normal, so we had to do dot plots for each of the samples. And yeah, I think they look pretty good. There's no crazy skew or outliers, so I think we're fine. All right, do step. Now, if you were doing this by hand, this is what it would look like. So, give you a little heads up. My daughter's texting me. See, if it's not my mom, it's my daughter. Okay. So what we would do is, we're going to do this anyways, but we would put group calcium in list 1. We'd put group placebo in list 2. And then you could run one variable stat for each of the lists to find the mean and the standard deviation, the sample mean and sample standard deviation. And obviously the count is just how many there are. But I'm going to show you in a minute how we could have done this whole thing on the calculator. But either way, you got to enter that stuff into list 1 and list 2. So if you're playing along at home, go ahead and do that. So enter all this into list 1 and all this into list 2. In class, we are most definitely going to do this. Now, again, if we're doing this by hand, they're going to have you take the statistic difference. So remember the order was calcium minus placebo. So calcium minus placebo would be 5 minus a negative 0.273. And that comes out to positive 5.273. Oh, minus 0, of course. Now down here we have our variances divided by n, variance divided by n, add them together and square root them, right? That's just the formula for using two samples. We have to find the variances and add them together to join them up. And eventually we get a t-score of 1.604. Cool. And then it's like, oh, do you want to use your calculator? Yeah, I do. So actually all that work we just did, we could have skipped. I'm going to show you in a minute how that looks. I know I keep saying that, but I mean it. So if we did the old school way of degrees of freedom off my table B, well, the smaller sample size was 10, right? So you're using degrees of freedom of 9. And remember, we're looking for that t-score that we just found, which was 1.604. And comes out to about 0.05. Okay. Now, this is not a two-tailed one this time. It's a one-tail. So 0.05. So a normal person would have not done that by hand. We would have used what's called a two-sample t-test for the difference in means. And it's going to give us a p-value 0.0644, and it's going to pop out the true degrees of freedom as being 15.59. Again, you don't need to worry about how they got that. Don't worry about it. So here's the big idea. Can you make a conclusion? So our p-value is greater than our alpha, which means we fail to reject the null hypothesis. The experiment does not provide us convincing evidence that the true mean decrease in systolic blood pressure is higher for men like these who take calcium versus men who take a placebo. So no evidence, or not convincing evidence, I should say. Now, one more before we get to the calculator. Interpret the p-value. So remember that p-value, I don't remember what it was, about 6%. That means, first of all, when you interpret a p-value, you go back to the null hypothesis and you claim that it's true. So assuming that the null hypothesis is true, assuming that there is absolutely no difference between the true mean, we still have a 6.4% probability of getting that difference, or even more extreme than that, just simply by random chance. And that's the reason why we failed to reject the null hypothesis. We had a pretty high probability, at least compared to alpha, of getting that result by chance, which means, it was just kind of dumb luck and variability. So it wasn't significant, statistically significant. I think that's a weak point in our class of us really understanding what the p-value stands for. It's just the probability that you would get those results by chance if the null hypothesis was actually true. All right, as promised, the calculator. So if you go to stat and over to test, you're going to see a lot of options, but one of them is called two-sample t-test. So two-sample t-test gives you two options, stats and data. So I forget what that problem was about. Oh, the work week problem, right? Where they said, like, here's all the statistics for like 1975 versus 2014 and how many hours everybody works during the week. So you would enter your data for, whoever you called sample one, and then also sample two. And you're going to just kind of enter those one at a time. A little laborious, but it's okay. And then you choose the appropriate alternative hypothesis. So remember that one was just that the hours were different than 1975 versus 2014. And then whenever it says pooled, for our class, always choose no. We'll talk more about that later. All right, so it's going to spit out this information, which I hate to break it to you guys, but it's the same exact information that we got. Actually, it's better than what we got because we're using technology, which is more accurate than the tables. So this is the t statistic. This is the p-value. Now watch out, there's a little e at the end of it. So that's the point. This is like times 10 to the negative 6 power. So this is 0.00000. I think I got enough. 115. Very small p-value. Notice the degrees of freedom are given to you here. And then it kind of restates the statistics, and it comes through, I didn't scroll down and get the rest of the screen, but it just kind of restates the statistics. So I know we've seen cases on FRQs where kids didn't really write everything down and still got credit. That makes me really nervous. So what I would like you guys to do is, if you're using this method, which I assume we all will, please, for Pete's sake, just write down what you're putting in your calculator. Because it'll help slow you down so you don't make a stupid mistake, but it also gives your reader a little bit of insight. Now, that previous example, did I get these backwards? That wasn't about work week. What was it about? Oh, my memory's shot. Okay, the calcium problem. So in the calcium problem, they didn't give us statistics. They gave us data. So I need to probably change that. So what we would do is we would enter our data into list 1 and list 2, which, if you remember, I had to do that anyways to find the sample means and the sample standard deviations. So like, if I've already entered them, then why am I not doing this? So in this case, you would choose data, put your data in the right spot and tell me where it's at. Frequency for us is always going to be ones because we're not going to multiply the list by anything. And then the appropriate alternative hypothesis was that, remember, we set it up where the calcium group had a greater decrease than the placebo group, so that's why we chose greater. Always choose no for pooled, and then you have a choice of calculate or draw, of course. Calculate is probably better at first because it gives you everything you need. So here's your alternative hypotheses. Here is the t-score, the p-value, degrees of freedom, and then it just kind of restates everything that you would have found by hand. Now this is why I like this method. Sample mean, sample mean, sample standard deviation, sample standard deviation. So it gives you everything, a one-stop shop. I prefer this by far than doing it by hand. In fact, I think there's a slide coming up that, right here. often leads to calculation errors by students and their teacher. So in order to avoid that, your teacher might recommend that you use the two-sample t-test. Heck yeah, I am. Make sure you name it the proper name though, guys. It's a two-sample t-test for mu sub 1 minus mu sub 2. Now, if you called your mean something else, like mu sub c, mu sub p, then go ahead and refer to it that way. That's fine. And then in the plan step, make sure you've listed that out. And in the do step, make sure you've given all of the important information. Okay? So more is better, in my opinion, on those. Just write down everything you possibly can that you think might be helpful to a reader. Okay, so about that pooling thing. The only reason we would want to pool our data is if we know that they have the same variances. So when you move on in stats, sometimes you'll have technology where they give you two options. They'll say unequal variances versus equal variances. And that's what the idea of pooling is about. So unequal variances means that you cannot pool your data together. So they do a procedure that allows you to do the two-sample t-test for the difference in means, regardless of what your variances are. If your variances are the same, then you're allowed to pool them together, and it makes your stats a little easier if you're doing it by hand. But if we're using technology, then no, we're not going to do that. So our recommendation in your book is just to never use the pooled option, because even if you could pool them, if you don't pool them, it's still going to give you the right answer. And what do you care? Because you're not doing this by hand. All right, water break, time out. Oh, I kind of love this problem. It's so stupid. Okay. Oh, I shouldn't say that. Two students made this their project. My bad. Sorry, kids. Two students performed an experiment to determine whether plants would grow better if they were exposed to classical or metal music. Yeah. All right, so 10 bean seeds were selected and each were planted in styrofoam cups. Half of the cups were randomly assigned to be exposed to metal music every night, and the other half were exposed to classical music. I just would love to be at the house where the parents are like, "Why are you playing metal music all night?" Like, "Mom, it's for my stats project." Yeah, that'd be great. Oh. All right, so the amount of growth in millimeters was recorded for each plant after 2 weeks, and here's the data. 2 weeks of this? Oh my gosh, those poor parents. All right, anywho, so here's the data for the metal group compared to the classical group. Do we have convincing evidence at the 5% level? Blah, blah, blah. They want significance tests done. Okay, so pause the video. I want you to try this from beginning to end, and I highly encourage you to use your calculator, which means you're going to enter this data into list 1 and this data into list 2. But before you get to the do step, remember, you're going to need to do all the other parts, state, plan, check your conditions, all that good stuff. All right, here comes the answers. So we are going to test a null hypothesis that there is no difference and the alternative hypothesis that there is a difference, so that it does not equal 0. Now they're setting up mu1 to be the true mean growth after 2 weeks for the plants that were exposed to metal music. Excuse me, I'm sorry. Okay, and then this problem's really choking me up. No, I'm just sniffly. Mu sub 2 is the growth for the bean plants that were exposed to classical music. So we are performing a two-sample t-test for the difference in means. They were randomly assigned to be exposed to one music type or the other. They didn't, do that unrandomly, so that's good. Notice they did not mention a 10% condition. They did not mention sampling at all. That was the right thing to do. They are going to mention the sample sizes. There's too small, right? They're not 30. So when they look at the dot plots of the distributions, they're saying there's no strong outliers or skewness. And some of you are looking at this going, what? Say what? They're considering that not to be a strong outlier. If you ran the one variable stats on this and found out like 1.5 times interquartile range, it's not an outlier, so just trust them. All right, so on the do step, if you're like Mrs. Abruzzo, you are literally skipping every part of this, and you put the data for the heavy metal music stuff into list 1, and then the classical music into list 2. So then when you run a two-sample t-test, your calculator is going to give you x1, s sub 1, and then there's 5 of them, and then same thing for the classical group. You don't have to show this work if you're using your calculator, but if you did it by hand, cool. Your calculator should give you something very darn close to this, if not even more accurate. And then your calculator also is going to give you a p-value of this with the degrees of freedom of that. And again, that was not me doing anything. That was 100% on the calculator. Now, if you drew it, you know I love that. So remembering that this is a two-tailed test, and this is a t-distribution with degrees of freedom of 6.88 that was stolen from the calculator. Now, if you were a little old school, you would have used degrees of freedom of 4 because the smaller sample size was 5, so n minus 1 would be a 4. And then the p-value in that case would have been between 0.10 and 0.20. So, potato, tomato at this point, we're going to get the same overall conclusion. That's not the issue. We're going to get a p-value of this guy got 7% and this guy got about 10%. So again, calculator using this method is far more accurate because of the degrees of freedom and table issue, but food for thought. All right, so our conclusion, our p-value is greater than our alpha in both of those situations, so we are going to fail to reject the null hypothesis. We do not have convincing evidence that the true mean growth of plants like these that are exposed to metal music at night will differ from the true mean growth of plants that are exposed to classical music. Groundbreaking stuff, kids. Keep it up. All right, so this next idea is, it's not complicated if you start wrapping your brain around like when would this be used. So we're going to perform significance tests for a mean difference. And this goes along the line with what we still call like a matched pairs design for experiments. So we saw this in the confidence interval chapter 2, where like we had twins and we would compare the twins, identical twins data together. Or we would do like, you are a subject, but I'm measuring something from you before and after. So you're calculating for every single subject you have a difference within the subject. So whether it's a before and after or, with and without treatment just for that one subject. So this is a little complicated because it's a different type of inference. And I think a lot of kids see the diff and they think we're talking about difference of two means as far as two samples go. This is totally different. So the idea here is typically the null hypothesis, like always, is that the mean difference is nothing, that there is no change from beginning to end. You still have to check your conditions. Again, we have to think about what these conditions mean. So are they paired data coming from a random sample, or is it a randomized experiment? Okay, so one of those things has to be random depending on what it is. 10% would only be needed if you're sampling without replacement. Again, if you're experimenting, that's not an issue. And then large enough, meaning they both, you need more than 30 or more differences that you've calculated. Now, if for some reason you don't have that many samples or subjects, then you have to look at the sample data and make sure that there's no strong skewness or outliers, just like before. So, the good thing about this is the formula looks a little less crazy because you're really technically, this is like a one sample t-test is what you're looking at. I'll explain more about that in a minute, but the sample that we're really looking at is not the before sample, it's not the after sample, it's the difference between the two samples that we're going to calculate. So on our calculators, just to kind of give you a picture of this, you'll have your before group in list 1 or after, I don't care. The other group will be in list 2. And then in list 3, you're going to have it set up to calculate the difference between list 2 and list 1. So when we perform our statistics, it's going to be off of list 3. That's the tricky part, okay? So all in all, nothing here looks surprising. That's kind of good news, I guess. All right, so this is a problem that we're going to be doing together in class. They have 11 recruited volunteers for this study. It's an experiment, by the way. Each subject was barred from coffee. No, thank you. Okay. During one 2-day period, subjects took capsules containing their normal caffeine intake, and during another 2-day period, they took a placebo capsule. The order in which the subjects took the caffeine and the placebo was randomized. And obviously, they don't know. They're blind to it. They didn't state that, but I'm sure that's true. At the end of the 2-day period, a test for depression was given to all 11 subjects. So they wanted to know whether being deprived of caffeine would lead to an increase in depression. That's supposed to say the table displays the data on the subject's depression test scores. Higher scores show more symptoms of depression. So what we have here is subject number 1, and when they combined their data for when they took caffeine versus placebo, and they took their scores from their depression quiz, this was the person on caffeine versus on the placebo. Same thing for patient 2, same thing for patient 3 and 4, and so on and so on and so on. So I know at first glance this looks like 2 samples, but what's going to happen is each subject is like their own data point. So what we're going to do in class, I'm not going to be able to do it now because I don't have my emulator on this computer. We're going to enter, and it doesn't technically matter, but I'm going to put caffeine group into list 1 and depression group into list 2. Then we are going to, what's the next slide here? I'm going to make a list 3 that's going to have us find the difference between them. Now, the difference is defined right here in our state step. So the null hypothesis is that there's no difference between the groups, whether they took caffeine or the placebo. Oh man, I'm kind of looking over the data thinking, I don't know about that. The alternative hypothesis is that there is a difference that is greater than 0 because they're going to define it as placebo minus caffeine. So they're saying there's going to be a higher instance of depression in the placebo day versus the caffeine day. And again, try to sneak in that phrase for subjects like these, because when you have a volunteer experiment like this, it's only going to be applied to subjects like these. And then 5% significance level. Cool, because they didn't give us 1, so we go with 5. Now, for the planning, we are doing, this is different, so highlight this in your notes. This is a paired t-test for mean difference, okay? This is not 2 sample, this is a paired t-test. For my head, to keep the name straight, I think of this as a match pairs experiment, which is what it is. Although you're your own pair, so it's kind of weird. All right. Random, because they randomly assign them to treatments and also which, days they're getting the placebo versus caffeine. And then the samples are pretty small, so we had to check the data. And remember, the data we're checking here is not each separate data, like not list 1, not list 2. It's the difference, placebo minus caffeine. So that answers my question about what list 3 is. List 3 is going to be placebo minus caffeine. So if I put placebo in list 2, I'm going to do list 2 minus list 3. Remember how you go up into the name of the L3 and you can program it to do that for you? We'll talk about that in class more. All right, so now where this data is coming from, this would be if we, wrote down list 3, difference, 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 difference for all of them, and you found the mean and the sample standard deviation. And obviously there's 11 of them. Now your calculator would have done that also if you'd pulled up one variable stat for list 3. Again, doing this by hand, yuck. I'm going to do this on the calculator. Now, they're saying use TCDF with this t-score you just found, which would totally work. But guys, I'm here to tell you, we could have just done a t-test. Okay, we could have just done a, this is 1 sample t-test this time because we're using just list 3. So I would have done 1 sample t-test and then data. No, not data, excuse me, list. No, data, data, and say it came from list 3. And it would have spit out all the information I needed. It would have given me a better degrees of freedom. Well, no, it is 10 for degrees of freedom Abruzzo because it's 11 minus 1. Duh. Anyway, you're going to get a p-value close to this using that method on your calculator as well. It's going to be even a little more accurate. We'll practice that one in class. So regardless, we got to make a conclusion now. So our p-value is less than our significance level, which means we can reject the null hypothesis. I knew it! That's why I drank so much coffee. We have convincing evidence that the caffeine withdrawal increases depression test score, on average for subjects like these in this experiment. I am subjects like these. This is why I cannot give up coffee. I don't care what my doctor says. All right, so we have this giant check your understanding problem. It's huge, okay? So when we do this in class, I'm not going to make you type in all this data, but you sure could. But if you look at page 731 on your textbook online, you're going to see all this information. So what we're going to have to do is, I don't even have a picture of it. We have information about the pressure loss in pounds per square inch during the year of the tires. Each brand is shown in the table. Do the data give convincing evidence that the air-filled tires lose more pressure on average than nitrogen-filled tires? So the way they set up their significance test here is they're saying there's no difference versus there's a greater difference when you measure the difference in this order, air minus nitrogen. Okay, so for me on my calculator, I'm going to put all the air data in order in list 1. I'm going to put the nitrogen data into list 2. And then in list 3, I'm going to say air minus nitrogen. So list 1 minus list 2. And it doesn't matter what order you put list 1 and 2 in as long as you keep track of who's where. And we're going to do this at a 5% significance level. All right, cool. we are performing what's called a paired t-test because they're trying to pair up each one of those pairings that they made, so air versus nitrogen. And then check all your conditions. They were randomly assigned to be filled. The sample size was big enough this time, yes. And all this data from the sample, remember this is coming from my list 3. So the sample mean, sample standard deviation, all from list 3. This t-value I'm going to get from performing a t-test on list 3. So if you wanted to do this by hand, you sure could. It's not that hard. The sample mean you just got minus 0, the hypothesized difference. Standard deviation you just got divided by the square root of n. Okay, so remember the formula for a single sample, which is what we're really looking at here, is not too bad. The ones that are horrible are the difference of 2 samples. That probably was really confusing what I just said. I'm sorry. All right, so we have a t-distribution with a degrees of freedom of 30, because remember there's 31 matched pairs. So degrees of freedom is 1 less than that. And then, is I way out here, man? Ooh, we're going to get a tiny p-value, huh? Always so tiny that it even called anything other than approximately 0. So that's definitely less than 5%. That means we have convincing evidence. So we're going to reject the null hypothesis. We have convincing evidence that the true mean difference of air minus nitrogen in pressure lost is greater than 0. In other words, we have convincing evidence that tires lose pressure when filled with nitrogen. Lose less pressure when filled with nitrogen versus air on average. So this would be a claim for them to say, y'all need to fill your tires with nitrogen, and I'm sure they charge more money for that. It just seems like the right thing to do. All right, so now poses the most interesting question of the whole chapter. When do I use what? You've thoroughly confused me, Mrs. Abruzzo. Now what? So if you have 2 sample T procedures, that means data is coming from 2 independent random samples, from 2 populations of interest, or from 2 groups in a randomized experiment, okay? So that's where you're subtracting the means between each of them. That is different than using a paired T procedure. That's where you pair up the data from random samples, and it's always from a randomized experiment. So if you think you have a matched pairs design of an experiment, then you're going to be using a paired t-test, okay? Not a 2-sample t-procedure test, but a paired t-test. They are different, okay? So basically the idea is how did they collect the data? So keep that in mind. So here, they want you to figure out what kind of inference procedure should we be using. So in each of the following settings, decide whether we should use a 2-sample T procedure to perform inference or a paired T procedure. Isn't that the question, huh? There's actually like a huge thing we're going to do at the end of the class where not the end of the class, but as we study for the AP test, where it's like, name that inference test, because there's a lot of them, right? So it really comes down to vocabulary and your understanding of all of it. So before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fins that is supposed to be faster to remove. A customer advocacy group suspects that the time to remove the fins may be no different than the time to remove the old fins, on average. So 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot or on the right foot and vice versa. The time to remove each type of fin is recorded for every diver. So think about what's happening here. Each diver has one of each on the foot, and right foot versus left foot is randomly assigned. So what kind of a procedure are we working with here? And this is a paired T procedure because each subject, if you want to think of it that way, each diver is being subjected to both of the treatments in this case. I mean, you can call one the control group, like the old type of fin because they're used to it, but we got this new fin too. So you're going to compare the times for each diver on their, one foot versus the other foot. So that's why we have a paired T procedure. And the issue is the data comes from 2 measurements from the same variable. So time to remove the fin for each diver. This next example says to study the health of aquatic life, scientists gather a random sample of 60 white piranha fish from a tributary on the Amazon River during 1 year. As an elder lady here, an adult well into my years, I don't think I've used the word tributary since I was in 6th grade. I forgot about that one. All right. The average length of these fins was compared to a random sample of 82 white piranha from the same tributary a decade ago. So we have a group of piranha from the tributary right now. And then we have an average length of fish compared to a random sample of piranha from the same tributary 10 years ago. So we're comparing two different samples that we were collecting. So this is a case for two sample T procedures because you have two different samples and you're going to compare the two samples at the end of this. The data come from independent random samples from two different places, two different times. Well, same time, same place, different time. All right, can a wetsuit deter shark attacks? A researcher has designed a new wetsuit with color variations that are suspected to deter shark attacks. Oh my God, how are they designing this? Okay, bait. Okay, good. Oh. To test this idea, she fills two identical drums with bait and covers one in a standard black neoprene wetsuit and the other in the new suit. I got really nervous for a minute. I thought, who is volunteering for this study? Over a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum in the black wetsuit and the other 8 to the drum with the new suit. During each time period, the appropriate drum is submerged in waters that sharks frequent, and the number of times a shark bites the drum is recorded. Okay. I'm not sure I followed everything there. I'm going to reread that a little more carefully. So over a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum in the black wetsuit and 8. Okay, cool. All right. So, any thoughts on this one? Because this one kind of made my brain itch for a minute. I had to stop and think about that. So we're going to have data from the two different types of wetsuits that they're using. And that means it's a two-sample T procedure. If that's what you were thinking, you were right. That's the way I was leaning because I was thinking, okay, we got two different samples we're looking at. It's not like we took the bait chum and half of it was red and half of it was black or whatever. All right. So the data comes from two groups in a randomized experiment, with each group consisting of 8 time periods in which the drum with a specific wetsuit was randomly assigned to be submerged. So two sample T procedures. Very good. And that was the end of the lesson. All right. So we're really close to the end, guys. Chapter 12 is the end of the entire course. Chapter 12 has we're going to start off with talking about some more tests for our data, meaning chi-square test, which is important to AP test. And then there's some stuff coming up that's like a little less important, but I think we're going to have time to still go over it. That's the excellent news. We're almost done with naming all the inference procedures. So now as we start to talk about them, we have to really sit and think like, okay, do I have categorical or quantitative data? Do I have proportions or means? Do I have two samples or one sample? Do I have the difference of the means? It gets really complicated, and I know it. So we're just gonna have to practice it. That's the moral of the story. All right. Good luck, everybody.